Many of you know Bruce Hoglund, and Bruce, yes, great guy.
Thank you.
Bruce was
5-minute warning, right?
thorium before thorium was cool, man. I think you used to send out semaphore signals. You were so early to this, and then he had one of the first websites, like in 1990, didn't you?
95.
Didn't you have to chisel the web pages by hand?
If you look at it, I'm still a bad web designer, but it looks like crap because that was actually hard to do then. But
Okay. Well,
actually, that was the least significant thing I thought I was doing, because I was doing all this other advocacy, and I put it on the web as a throw-off, and the scientist said, "What's the web? Why are you doing that?" It turned out it was one of the most significant. So don't underestimate the little things you do.
I hear the internet's going to be big someday.
Like John said, I've been in it for a while. So my main goal today is to kind of pass on what I've learned and to show you how big this design space is. A Russian researcher once said that when he learned about molten salt technology, he goes, "This is like my garden in the spring. I can plant anything." Some of us think too narrow. If you want to be a designer, this is a lot broader than you think. I'm going to give you the bonbon road to core wall neutron flux suppression to enable a homogeneous Fast-MSR fueled by spent fuel and depleted uranium. That rolls off the tongue, doesn't it? Okay, last century, I'm going to make some predictions here. Last century was iron and steel age. I think the 21st century is going to be graphite and graphene. We're beginning to learn about graphene. MSRs are really all, and lifters, whatever you want to call them, are all about the plumbing. And really, MSR cores are boring. What salt? What graphite moderator in it or not? These are your two choices, you're done. MSR's action is in the heat exchanger, the pumps, and the processing. And last prediction is radioactive waste will become resources in the future, starting with spent fuel. Graphite. Graphite is key to what we want to do. This is a graphite crucible. As you can see, it's very solid. With molten salt reactors, they're crucial. It's an unknown that's becoming known because of our research now in graphene. It's been under our nose all these ages, but we're now starting to know it's mainly made out of graphene. It's compatible with all fluoride salts, and this has been industrially shown since 1889 with the Hall-Héroult cell, which is how we make aluminum. It has the highest, and I have a question mark there, melting point, because it actually sublimes before it melts, and that's at 3,825 degrees. It was the first filament for an incandescent bulb. It's one of the few materials that gets stronger as it gets hotter. Its max strength comes out at 2,500 degrees C. Put that in perspective, that's 1,000 degrees higher than the melting point of iron. And it's a mixture of the strongest and the weakest materials. Graphene is the strongest material we know of. This is graphite lubricant. It's one of the softest materials. Same substance. Again, it's a yin and a yang sort of thing. Just two factoids about graphite compared here. One is the thermal conductivity. As you can see, it's only 1/3 of copper, but it's far higher than stainless steel, and stainless steel and Hastelloy have about the same thermal conductivity. So graphite is a good conductor of heat. It also has the highest thermal shock resistance of any common substance, and this is great for heat exchanger design and other high temperature applications. These are some graphite things. You've already seen the MSRE. We can have the ultra purity of nuclear graphite, highly machined. You can see in the lower left-hand corner graphite is easily machined. It can be threaded, tapered, bored out. So it can be in a variety of shapes and sizes, and it can be very physically large, larger than telephone poles. All right. I don't have enough time to give you a full nuclear education here today, sorry, but I do want to talk about the nuclear resonance escape probability. And this is probably where, if you're not into geek, sit back, let lunch sit down into your stomach and take a snooze, I don't mind. All right, resonance escape probability is the term where it's the probability of a neutron, which is born at 10 to the 6, 1,000,000 electron volts. It travels at about 1/10 of the speed of light. So it's very energetic, but it's the probability of getting it from that high energy zone to the low energy zone, which is 10 to the 0 and below. That's thermal energy. You'll hear that referred to thermal energy. This is a logarithmic graph of the probability of the neutron interacting with plutonium-239. And as you can see, it's much higher in the thermal zone than it is in the fast zone. But plutonium is a rubbish fuel. If you look at it right where it's born, at that this line here, top line here, that's the fission probability. That's what you want to have happen. As you can see, as it slows down and going from that real violent-looking black area to the right, that's where most fast reactors operate. Most thermal reactors operate up here. And again, that's 100 times more reactive. You need less fissile, and that's why people like David LeBlanc want to make a thermal reactor. It needs less fissile. All right? The fast reactors need more fissile because it's less reactive, but you can see the plutonium reactivity goes down, and then there's a dotted line that's rising rather rapidly. That's the capture probability. That's what you don't want. But in my design, I want this, because this is how I protect the wall. These reactors have always had a wall lifetime issue. I think I've solved that problem. All right, neptunium is another common material you can have in the reactor. As you can see, its capture shoots up in the region of fast. And again, for me, this is a good thing. And what I've done is I've done MCMP modeling of this. MCMP, for those of you who don't know, stands for Monte Carlo N-particle software. And what it does is it allows us to calculate nuclear parameters and mainly criticality. I've done a lot of simulations, but I did 2 simulations for this group. Both of these simulations were using the sodium fluoride, actinide fluoride. The reason I use that is high solubility for actinides. Both of these reactor cores were 2.5 meters in diameter. This is about 8 feet. So 8 feet wide, 8 feet high, cylindrical geometry. Around that, you have a 1/2 meter going around that, and this is the bonbon. I'm going to get to the bonbon because that's the magic stuff. Both had the same 1/2 meter thickness. One had the bonbon type, and then I modeled the traditional pure graphite wall. All right. The way my system works to protect the wall is it's called core flux suppression. These neutrons are the agent of the fissioning process. If we absorb them or we get them to not cause a fission, then you lower the power. And if you don't have nuclear power in that area, no fissioning, you don't have damaging neutrons, your wall lasts longer, okay? So what I want to do is partially slow down the neutrons, like that graphs I showed you earlier. I want to get it where it actually absorbs, which traditionally you don't want, but I want to do this along the wall because I want to protect the wall. So I'm going to show you the 2 graphs of, the first graph is going to be the radial and axial flux in each MCMP zone. And I'm just plotting 3 zones: the center of the core, the wall of the core, and then the outer shell of the salt, and then which is right against the wall, and then the wall. Okay, this is called a flux graph. It shows the amount of neutrons per source neutron at the various energies. This is considered a fast spectrum. A lot of people don't think you can have a fast spectrum in fluoride. You can. And as you can see, the dark line at the bottom there, that is significantly lower. Again, this is logarithmic graph, so just about an inch on that screen is going to be a factor of 10 difference. So it's a big drop, and that's the wall's protected. Now this then is this is a busy graph, I apologize. This is now the same modeling except with graphite, and as you can see, the dark line here is the graphite wall, and it has a much higher damaging flux, so it's more damaged, and it's about a factor of 4 damage, so that's what we're going to expect. The wall is going to have that much shorter lifetime. This is a power graph. It shows you the various zones, how much power is being produced. Again, the green is the bonbon, the black is the graphite. And as you can see, it's a factor of 3 power at the end there. And the overall power density from center to outer is about 7 power. Those peaks are where you have fuel salt return. And as you can see in graphite, it's really horrendous amount of power in those fuel salt returns. So we can't use graphite in a big thick graphite in a fast reactor is the bottom line. All right. Now that you have a nuclear education, let's become paper reactor designers. All right. One of the problems with molten salt reactors technology is it really gives you too many choices. I mean, there's over 5 salts we could possibly use, maybe 10 or 20. So what salt becomes a big issue? What geometry? Spherical, cylindrical? But this third question is the most important. What purpose? What market are we building this reactor for? And too few people ask that question. Because if you don't have a business model, you don't have a reactor. Because do-gooding is not a business model. So think about what you want to do and then design your reactor. We've been doing it backwards, a lot of us, for a while. All right, what molten salt? To answer this question, I gotta answer that third question, the last question. And the business I'm going to choose here is I want to safely store spent fuel and release its energy. Why? I think there's paying customers, demand for it. That's my business guess. Yours may be different. The USA, and this is going to be USA-centric because I'm an American, we also have the world's largest inventory of spent fuel. We have 70,000 tons. By the way, this was going to be Yucca Mountain's statutory limit. It's going to be reached in 2015. So Yucca Mountain was going to be finished filled in 2015. So for those of you upset over Yucca Mountain being canceled, it really doesn't matter because we would have needed Yucca Mountain too. We also have 700,000 tons of depleted uranium, and the world has 250,000 tons of spent fuel worldwide. Put this in perspective, each ton of spent fuel has about 10 kilograms of plutonium. That's enough to make a warhead, a weapon that will flatten a city. So the world has 250,000 warheads worth of plutonium, and it's growing 4% a year. This is a growing problem worldwide. Okay, we're going to now store, this is spent fuel in its various forms. When you take it out of the reactor, it has to cool for 5 to 10 years. If you don't, you could have the Fukushima, that's bad. So what we're going to do, since we don't have Yucca Mountain, we're going to do that fuel cask, which is on the right-hand side. Plutonium's half-life, the plutonium-239 I showed you, its half-life is 24,400 years. So it's going to be around for a while. The cask is designed to last 50 to 100 years. See a problem? Okay, let's narrow down the choices. The salt, for my business model, the salt should have significant amounts of uranium and plutonium to store the fuel. The market says actinides and even fissile materials are no longer resources, they are waste. If you're going to bury something in a mountain, it's a waste. Safe storage is what paying customers want, and electricity may help pay for this storage. Capital costs must be kept low. So I basically want to do that silo thing, except I want to produce maybe some energy as a byproduct. All right, further narrow down the choices. The fuel salt has to have high uranium and TRU solubility. TRU stands for transuranics. It's plutonium and above. Thermal spectrum reactors have very low fissile inventories, and thus they have low uranium and TRU storageability. The fast spectrum requires 5 times more fissile than thermal. So I'm going to build fast reactors. David's going to build thermal or slow reactors. He's going to be 5 times wealthier than I am because that's how large his fleet can be. It's 5 times larger than mine. But right now, it's a waste, so we want to store it. All right, fast spectrum burns spent fuels, actinides the best, and the fast spectrum is easiest to breed in if you want to breed. That is, make new fissile. This is going to come up, so I'm going to address it. I'm not a fan of chlorides. Chlorides allow a faster spectrum than the fluorine. However, this can be a proliferation issue. For example, the French general 5 to 10 years ago confirmed what a lot of us believed. The French got most of their military plutonium from their liquid metal fast reactors. So if you have too fast a spectrum, you can make military-grade plutonium. My spectrum that I just showed you is a crap spectrum as far as fast goes, so it makes crappy plutonium, as I'll show you later. So chloride's one advantage is not needed today. The world is awash in fissile. We have excess military and commercial fissile we need to get rid of. There's more chlorine negatives than positive. Chloride corrosion is less known. It can't support a thermal spectrum like David wants to do. Chlorine 36 is going to be produced. Oh, you're kidding. I got to speed this up here. All right, this is I apologize for this. This is the salt I want to use. Sodium lithium fluoride. It has high uranium and actinide and plutonium solubilities, and it gives you a wide range of temperatures you can operate at. I want to go back to the future. I want to stack a bunch of blocks, just like we did a few miles from here, to create a reactor. If you see there, this is graphite. That's graphite, just with holes drilled in it, and they put uranium, and they stacked it up, it made a reactor. Couldn't be much simpler. It's called Chicago Pile, that is pile of blocks, 1. It was the first reactor a few miles from here. This is my bonbon brick. You've probably been wondering what's a bonbon. Take graphite, put thorium, mainly thorium tetrafluoride in there, put a little uranium tetrafluoride, and lock it up. I show cylindrical and hexagonal geometries, and then what we're going to do is stack them in various arrangements. We can create reactors just by stacking it. The one difference is I'm going to have fluoride salt in there as the fuel, not uranium slugs. One other thing I'm not showing here is you have to have the Hastelloy wall around the outside. I like thorium fluoride because it has high density and a high melting point. 1110 C, that's higher than copper or silver melting point. So it's a very high melting point, and its density is 6.1. The density of steel is about 7. So it's a very heavy, dense material. This is another design that I always thought of. I want to get rid of the pipes. I want to get rid of all the tubing and all this stuff. I want to have a nice compact design like David was showing, the smarter. This diagram, I can't remember where I got it, but it's 40 to 50 years old from Oak Ridge. I modify it by I take out the center core, and I'm not going to have any Hastelloy or anything. I don't want to even pump the blanket salt around. All right, we'll go through here. This is my design. This is the core. Comes in thermal or fast. Fast has no moderator in it. If you want thermal spectrum, all you have to do is put graphite logs in there and it will become a thermal spectrum. The green is the bonbon salt. The gray is the graphite. And the salt flows up through there. It's lifted by gas lift, but you could use a conventional pump. Again, this is my wish list of all the things I'd like to see in the MSR. The heat exchanger is made out of graphite. If we can do that, we can get 700 to 1,000 degree output temperatures. This is how it would be emplaced underground. The reactor core would be lifted up because that's the part that wears out. Graphite does not suffer creep, so it's conceivable this heat exchanger could last 50 to 100 years. The salt is pneumatically in place. You blow gas down in the bottom thing. It shoots the salt up into the tube. No more freeze valves. This operates much quicker. It fails safe. If you remove the pressure, the salt goes back into the drain tank. And as you can see, the drain tank is full of bonbons to make sure it's subcritical down there. That is, you don't have a nuclear reactor occurring in your drain tank. You don't want that. You then cart it away. Bring in the new core, lift it up, replace those broken elements, and off you go. All right, recapping the advantages. This is a results of the simulation I ran. It's a 12.5 meter core volume. The salt's there. The breeding ratio in the core was 0.92. The total breeding ratio was 1.14. So most of the breeding is being done in the thorium. You're making a lot of U-233. If you run a gigawatt year, that's about 140 net kilograms of U-233 every year, and you only have to then take and put about 80 kilograms into the core every year, and that's for 1 billion watts 24/7 for a year. All right, this chart shows the DMSR at the top line, and I put that in comparison. Its core power density, its salt power density was 27 kilowatts per liter or 27 megawatts per cubic meter, whatever your unit of choice is. They work out the same. You can pretty much follow it along. I assume a 50% thermal efficiency. That's probably generous. The specific power is a calculation of the efficiency of your using fissile. That how much inventory do you need to produce a certain amount of electricity. In this case, a higher number is better because it means you produce more electricity for a given amount of fissile. And then I have a ratio, how much worse is it than the DMSR? The DMSR is a sweet reactor. Like David said, that is the one to beat. If you're going to be a paper reactor designer, you've got to beat the DMSR in my opinion, because that's such a sweet design. All right, the total electric power install is if we took all of Yucca Mountain's nuclear materials and we started fueling a DMSR. Well, how many DMSRs could we have? Well, it turns out we could have about 400 gigawatts worth of electric power. Put that in perspective. And again, sorry for the American perspective only, but America has about 500 gigawatts of power. 20% is nuclear, so that means 100 gigawatts is nuclear right now. So with the 400 from the DMSR, the 100 from current, with just using Yucca Mountain, we could refuel all of our electricity from a DMSR, LWR, 100% nuclear electricity, and we just have to keep the LWRs fueled. The breeding time, doubling time is there. The interesting thing is, now, oh, by the way, the wall lifetime is 41 years of my bonbon design, so the core flux suppression works. Let's say we would want to we're willing to go down to 5 years of wall lifetime. Now, I don't know if that's desirable or whatever, but look at the amount of power we get. At the power density is 414 kilowatts in 1 liter. So look at your liter water bottle, 400 kilowatts being generated in there. Whether that's practical, I don't know. The wall can take it, but that's pretty cool power. That's rocket density power. If you can do that, then that one 8-foot diameter, 2.5 meter core can produce as much electricity as 3.5 large light water reactors. And its doubling time goes down to 10 years. It actually becomes more fissile efficient than a DMSR, which again is the one to beat. Now, whether we can do that, I don't know. What we're going to do is build one of these. If we do, make it small, and we're going to then, and the way you just change the sizes, you just change how fast it's pumped. The core can stay exactly the same. All you have to do is pump it quicker, and you'll get more power. That's it. So again, I said at the beginning, the action is in the heat exchanger, the pipes, and the processing. That couldn't be more boring. This is a D chart. Hopefully this, I'll end up putting this online so you'll be able to get it. This is the amount of isotopes destroyed or produced per fission that occurs in it. As you can see, it's a uranium-238 burner. There's no thorium in the core, but there's a lot of thorium in the blanket. Matter of fact, there's 2 times more thorium in the blanket than there is in the core, and it's simple geometry. It's consuming the thorium down there. As you can see, it's building up the U-233 there, and it's not producing hardly any of the long-lived TRUs, and it's also destroying that problematic Neptunium-237, which, while it has uses for making plutonium-238 for the space program, that's tiny. It is a long-lived waste, and it's also proliferative. You can make a warhead with neptunium, so that's it.
Ta-da! That's great, Bruce. I've never saw that before. That's great stuff.